Coming up next on the IP Talk stage, Paul Hollingworth from eSilicon presenting Chip PPA Optimization with Custom IP.
Thanks for taking the time. My name is Paul Hollingworth. I work for eSilicon, and what I'm going to be doing is talking about chip power, performance, and area optimization when you're building custom IP. See if this works. There we go. So what we find now is that the majority of big designs are typically over 40% of memory. So the total area, over 40% of it is becoming memory. And so what you'll find is that over time this is increasing. So this shows from 99 to projecting to 2017. And you can see in green is the percentage of a chip being designed now, which is memory. And so you can see that exceeding the 50% mark. And it's kind of interesting because if you think about memory design, it isn't something people have really concentrated on. Since we got good compiler technology, people take it for granted that the compiler produces a good result, and then that's it. But what we find is that as you get all these different types of memory, and as the percentage of memory increases, it actually becomes very important to optimize that memory. Not only does it dominate the area, but it impacts the power and the performance, and potentially the manufacturing yield as well. So what eSilicon does is produce custom ASICs. And we do it for a range of customers, and you can see some of them up here: Broadcom, Qualcomm, Huawei, Avago, Tektronix, and so on. But you won't see our logo on parts because we always put the customer's logo on there. We have three divisions doing IP, ASIC, and what we call SMS, Semiconductor Manufacturing Services. And we work with a range of suppliers in the foundry space, test, package, and assembly, but also for IP, EDA, and even design services. So sometimes, for example, in silicon manufacturing, we will be responsible for taking over an existing design and then making sure that it runs smoothly through the factory, through the test and assembly, and gives a good yield and so on. And we do that a lot for fabless chip companies. But our main area of business is ASIC. And increasingly, what we're finding is that it's very useful to have an IP group which is able to optimize the IP for the ASIC. So we do that typically for the ASICs we produce, but we also do it and sell that to other companies who just want some customized IP. So here's a couple of examples. I'll show this one first. This is a DTV, digital TV application. And this represented a chip that was 40% memory with a lot of instances, 2,500 plus instances, and 525 different unique types of memory. So you look at that and you think, well, you can't optimize all of those. That's too much work. But actually what you find is that just by picking the 21 instances that are used most, you can save a significant amount of area. So what we were able to do was to save a total of 5 square millimeters of chip area, which in a consumer product makes a significant difference to the cost. And the kind of area reduction techniques that we were able to use: circuit and layout optimization, removal of unnecessary circuitry. A lot of the compilers put things in which give you a lot of flexibility, but if you don't need that particular functionality, then it's unnecessary. Changing to a smaller bit cell was something we were also able to do. And then probably the biggest portion was we had a lot of memories that were 1K by 32. And by merging them into a single large L2, that saved 2 square millimeters just by itself. So all of these changes are quite small incrementally, but they add up. and a 5 square millimeter difference in a consumer chip, which is quite a large chip, this particular one, was a very good cost benefit for this particular customer. Another thing that we find that custom memory is very good for is speed. And one of the things that's happening now in custom chip design, as I'm sure you're aware, is there is more and more processing going into these custom devices. And in some cases, that's a multi-core. So, we're beginning to see now the first quad-core designs coming out in phones. But it's not just the main core that we're talking about here. In many cases, there are processing elements which you can think of as accelerators. And each of those requires some kind of access to cache or memory somewhere on the chip. And what we've seen over time is that as we go down the technology curve, the prediction is that for 22 nanometer networking chips, you'll be looking at something like 80 plus cores. That doesn't mean 80 ARM or MIPS cores or Intel cores, but these processing elements, there will be a lot of them on there. And so optimizing the caches for these can make a very significant difference in the overall performance that you'll see. This is a good example of that kind of optimization. So this represents a chip that we did along with MIPS and with Global Foundries. This taped out in August last year on their 28 SLP process, which is a high K metal gate, but low power process. It's an interesting process. And this actually represents 3 different MIPS cores, along with a cache coherency manager and an L2 cache here. And so this isn't a large piece of silicon, but it was very performance critical. And what we found was that these are based on MIPS's 1074K core, which is their highest performance core, which is currently shipping. And the critical path for the execution of these cores was definitely the L1 cache. And it was slowing the performance down. So this was the most performance that we could get out of a standard compiler. So by doing customization, taking out circuitry that we didn't need, optimizing the memories, we were able to speed this up by over 30%, with the net result that we met a worst case performance, so at 0.9 volts, slow, minus 40 degrees C, of 1 gigahertz, and the typical is around 1.5. And we think that's important because if you just look and extrapolate what's happening to the performance requirements of these processors that are going into the high-performance phones, the smartphones and so-called super phones, and we can see that at the 20 node, we're going to be needing performance of around 2.5 gigahertz. And in that case, it really is going to be memory performance, specifically cache memory, which is limiting a lot of what we can do. What about power? So I've talked about cost and I've talked about performance, but power, of course, is very important as well, particularly with anything portable. And it's interesting now that as we go to the 28 nanometer node and ultimately below, what we're finding is that it becomes extremely complicated to work out what the best solution is for power. So I won't explain all of these lines, but what this represents is the delay of a 2-input NAND gate plotted in HVT transistors and standard VT transistors. So what you'd expect is that to get any kind of acceptable performance from a leading edge technology like this, you would need to use SVT transistors. You would also expect that you wouldn't want to increase voltage because power is always proportional to voltage squared, as we all know. And yet what we actually find is that by taking HVT transistors and overdriving them, we can get the delay down to the point where it is as good as the SVT transistors, but you're actually using less power. So this is a kind of counterintuitive result, but it's the sort of thing that we're finding more and more in these very detailed analyses that we need to do in order to get the right result from the chip. So this is a real example. This is a network processor. that we worked on, and the challenge here was to get the same performance but to reduce the static power particularly. So this is a 28 HPM TSMC design. There's a large amount of memory in here, nearly 400 megabits. And what we did here was to take the standard VT memory array, and then we migrated the peripheral logic to HVT. So you can see here on the left, this represents 3 different types of memory that we were doing this for: dual port SRAM, a 2-port register file, and some single port SRAM. And you can see that the real problem here was the periphery leakage. So this was around 12 watts. So total leakage for that particular memory was nearly 15 watts. And by using these high VT transistors, we were able to reduce this significantly. So we went down by around 20%. So that doesn't cost you anything else. And by the way, when I say overdrive, this means not that you're going beyond what the technology itself is capable of. So this is within the reliability threshold that the foundry, in this case TSMC, approves of. So you're still talking about a 10-year lifetime on these products. So that's power, area, and cost, and performance that we've been able to show that we can improve. So this is obviously just a very quick talk, but please come and talk to us, check out the website, and we're very interested in talking to people about their next chip. Thanks very much for your time.